Thank you, Professor, for inviting me. And I am really pleased to meet all of you, and I hope there will be time to meet in person. And moreover, I would like to thank you all for hosting me for my internship. Today, I will introduce you to some topics I covered within the last months during my research activity. This is just a brief outlook on what will be the main fields I will present you. And despite the mere signal processing perspective, I would like to give you a specific perspective, which is that of edge computing. As Professor Eleni told us before, I work on the employment of sensors for the SMM system. And in particular, all that the signal processing functionalities and techniques are meant to be embedded within the sensors which commonly use for SMM purposes. And in particular, this could be possible thanks to the digital signal processing which we have on the sensor boards. And the reason why that was possible was due to the development of miniaturized smart sensor nodes. These are devices which are likely a small stamp, and they specifically integrate a MEMS-based inertial measurement unit, which is a MEMS digital accelerometer, and moreover, it includes also a 3-axis gyroscope. And the specs of such an element are compliant with most of the requirements in typical vibration-based scenarios. And the enabling principle of such a device, despite the sensing element itself, is an STM32 microcontroller unit, which has on board all the electronics and the circuitry which enables it to gather data, locally preprocess them, and then forward and output the final information which is retrieved to a remote connected station or a cloud server. And the typical way we use such kind of sensors is that of deploying them in a clustered manner. Clustering means that we divide sensors in subgroups of sensors, each of them which are managed, administered by a local cluster head. Some processing is thought to be performed locally, and then the information which are computed are forwarded to the central aggregator, where the whole modal information is merged and the final integrity status can be retrieved. So all of the signal processing I will present to you in the following are thought to strive and enhance the functionalities of such devices, because as we may know, there are some issues which need to be tackled, which start from the electrical and power consumption of these elements. And moreover, we would like to reduce the distance which usually occurs between data and the finally retrieved information. So the first topic, which is compressive sensing, is specifically targeted to the enhancement of the data payload and the communication bottleneck, which usually occurs in SHM system, especially for large structures. Compressive sensing is an analytical method according with which we can reduce the dimension of the signals which we are actually acquiring in order to work and to fully exploit what is a typical pattern which is perfectly met in the case of a vibration-based SHM. Indeed, what we know is that the information associated with a structure is usually confined below a small couple of modes, which are the most energetic component. So if we suppose that a generic signal which represents our acceleration data is sparse in a given basis, and that basis is usually, for example, a Fourier basis, we can exploit the fact additionally that such information is not uniformly distributed in the whole signal domain, but the energy tends to concentrate in specific part of our spectrum. So the reason and the idea we tried to exploit in that sense is how can we maximize the performances of the compression itself by capturing as much energy as possible from our input signal. And in order to solve this problem, we resorted to a Rakeness approach, which is a method already presented in the literature specifically for biomedical signals. And that method increases the compression performances by summing together both the sparsity, which is the classical premise of the compression sensing perspective, with the localization itself. And what the Rakeness problem does is to define the sensing mechanism, namely the matrix we use to shrink the dimension of the input signal by solving an optimization problem which maximizes the Rakeness quantity, where the Rakeness quantity is defined as the average energy of a projection of instances of X, so of our input signal, over independently drawn instances of Sj, where Sj represents each row of the sensing matrix. But additionally, what the method does, which is its peculiarity, is to purposely tune what should be the localization exploration trade-off. So it purposely defines to what extent the correlation profile, so the energy distribution, let me say like this, of the sensing mechanism should superimpose to the localization of the input signal. The problem of the Rakeness constraint is solved by defining what should be the correlation profile of the sensing matrix, according with which the consequent row of the sensing matrix itself can be defined. But as you may understand, following all this workflow, what is the most important parameter, first of all, of that method is the definition of the input signal correlation profile. So we need to estimate Kx if we suppose that Kx is that distribution profile in a way that is fully representative of our process under analysis. And in order to solve this task, we have considered two different approaches. The former one is a fully data-driven approach, which only depends on the acquisition of in-field measurements. And thus, once we have collected as many signals as possible, we can resort to its classical definition to compute Kx. Differently, we have recently investigated a novel method which we can name a model-assisted approach, according with which we can exploit prior structural information to define in a synthetic manner what should be the correlation profile. Specifically, if we suppose that we know or we can imagine what are the vibration frequencies at which our structure will vibrate, we can define, according in correspondence of its frequency, what should be its corresponding frequency width. And then we can resolve the Rakeness problem in a simple manner. For example, let's consider that a toy case in which the black dotted curve represents our current and original correlation profile. What should be the correlation profile of the classical Rakeness statement is provided by the red curve, which is perfectly matched on the black one. Whereas, on the contrary, what the model-assisted approach does is to tune and to enlarge the width around its peak in order to be more robust with respect to possible variations in the frequency distribution. Indeed, we need to make more robust our identification and our compression in order to counteract possible detrimental effects, which could be either the consequence of structural deterioration or environmental and operational conditions. Just to recap, these two methods have inherently some pros and cons, And despite the totally unsupervised nature of the classical Rakeness implementation, it obviously depends on a huge amount of data which needed to collect before defining a KX in a proper manner. On the contrary, the MRAK approach is highly adaptable, but it requires a certain amount of information before it can be fully computed. Moreover, since the compression performance does not depend only on the sensing matrix, but also on the sparsity, namely on the domain in which we suppose our structure is sparse, we tried to optimize the sparsity ratio itself. And in that case, the idea was to find a specific time frequency plane in which our input signal must be optimally sparse. In that case, we resorted to the wavelet packet transform, which is a classical signal processing technique which decomposes an input signal into sub-different signals, each of them carrying half of the spectral bandwidth of the input instance. But in more detail, VPT operator acts in this manner as it is schematically represented here. If we suppose that we have an input signal, what the VPT operator does is to process in parallel that input signal with two different filters, a high-pass filter and a low-pass filter, which, as I have mentioned before, carries half of the number of samples and simultaneously half of the bandwidth of the original data. And this is summarized in the approximation and the detail coefficient, which can be straightforwardly computed by means of a scalar product between the input signal and a corresponding wavelet packet, where the wavelet packet strictly depends on the selection of another wavelet, which is a specific function which should represent the fitting between our signal and the way we process it. And in that case, which is just an exemplary case, we can correspondingly obtain a time frequency plane in which we have a specific framing where each frames represent a specific wavelet packet at a given instance of time and a corresponding location in frequency. But the reason why we selected such kind of operator is that it allows for a purpose pruning of that decomposition tree. So the versatility of the VPT operator is that of cutting some branches of our decomposition in order to match what should be the high or low frequency resolution according to the spectral distribution of the input signal. So once again, suppose that we have such a kind of input signal correlation matrix. What we can do is to apply a center divide and conquer algorithm according with which we can first of all retrieve what should be the optimal decomposition depth. Once we have obtained, according to that decomposition, the full wavelet packet tree, and we can merge together those wavelet packets, so those final packets which belong to a further packet, so which belong with a higher level of decomposition, does not rely to the frequency band of interest. In that case, what we can obtain is a different time frequency tiling of our structure, which increases the frequency distribution in the region in which we expect to know the information will be present, and it relaxes the frequency constraint in favor of a more specific time localization in the corresponding bands. Apart from the optimization of the sparsity, which serves that preliminary task in a vibration-based SHM when implemented on sensor, we tried to approach another important aspect, which is how can we infer the current health status of our structure? And in order to provide a response to such a question, we started to investigate different diagnostic algorithms. And the first instance was the implementation of a one-class classifier neural network, which is a neural network thought for damage detection, where the output is to provide if a specific initial condition belongs to an unhealthy or healthy status. What the workflow of such a one-class classifier neural network includes are some preliminary steps. First of all, once we have collected all the instances coming from our sensors, which we suppose to be organized in a matrix, we can perform some preliminary stages such as filtering, downsampling, or why not even compression. Then we can enter the classical modal identification phase in which the modal information is retrieved, for example, by resorting to stabilization diagram, which obviously needed to be cleaned in order to define only what are the stable poles. Such an operation can be repeated the number of times, which is equal to the number of instances we have as input. So as well as the number of different measurements we have performed. Once we have such kind of information, the frequency tracking space is entered, in which we shrink the dimension of the whole amount of possibility in terms of frequencies that we have. In that case, frequencies can be clustered, and the information which is retrieved can be tracked over different amount of time, for example, by applying moving average filter. Then, once we have all such a kind of information, we can compute what is the density in the whole feature space, and according to that density, to generate adversarial point in all the space or the feature space which does not belong to the current distribution of our data. So what the adversarial point generator does is to generate points outside the boundaries, where the boundary defines the limit in between a healthy and unhealthy point. And according to these two kinds of data, the healthy and unhealthy one, we can train a neural network to learn what are the boundaries in between the two different labels. And by iterating this process a number of times according to what we think it should most fit best, the resolution in between the healthy and unhealthy condition, we can finally output with the estimated boundaries. And such boundaries can be further used to classify different health conditions as new instances come into the system. And despite the classical problems or the classical criteria which can be followed in implementing this kind of neural network, we started to reason about what can be problems in real use cases. And one fundamental issue is related to the influence of environmental and operational parameters. And in that case, we needed to counteract for them, for example, in the OCCNN implementation, and we thought about two different possibilities. The former one is to provide such kind of parameters as additional input features of our system, and otherwise to pre-compensate them by means, for example, of a dynamic regression. Differently, we can try to exploit different ML approaches such as KPCA and ANN, which conversely try to find nonlinear boundaries different directly from the retrieved information. And the last question was, is it possible, since we have availability of compressive sensing algorithm, to combine them in an ML approach? And the further question is it possible to avoid the dependence on modal-based information, or it is such kind of frequency tracking still necessary to reach a good estimation. And in order to give a response to some of these problems, we started to verify how could the influence of, for example, the compression approach be on the quality of the estimated status. In such case, we have considered the benchmark use case of the Z24 bridge, and what you can see here, despite the near implementations, is how the compression approach may act on that information. In the first row, you can see what is the result of applying the ANN and KPCA algorithm directly on the raw dataset, whereas in the bottom line, you can see how this feature may change when we apply a compression stage. In that case, we have considered the model-assisted approach with a compression factor equal to 6. And moreover, the information in terms of frequencies which were used to define the input signal correlation profile were the frequencies that directly derived from the literature. And what we can see in terms of a numerical result is that even after applying compression, we are capable of identifying the correct alpha status, but at the expenses of a lower precision in our classification. Finally, we tried to solve another crucial point in the monitoring of mesoscale or large structures, which is that of combining together model parameters which are obtained in different clusters, so in different subgroups of sensors, as I have mentioned before. So supposing that we have such kind of an implementation, the final objective is to merge together what are the different, for example, modal shapes which we can retrieve in each cluster-related processing step. But what the literature suggests up to now is to ensure a bit of overlapping between different clusters in order to make the model merging procedure as much accurate as possible. But this has obviously some limitations, both in terms of electrical, computational, and technological way. So in order to solve this task, we tried to apply a completely different paradigm and to move the complete model merging problem into a graph domain. And the enabling reason for such a translation is the fact that modal shapes are inherently smooth modal curves. And this characteristic perfectly matches with the intrinsically smooth graph signal behavior at the basis of the graph signal processing. But let's go a step before, and generally speaking, a graph is a structure which is composed of nodes connected by vertices, and the edge which connects vertices, different vertices, defines what is their relation, their level of adjacency. So the idea in that case is to account for spatial disjunction by means of properly tuned graph weights associated to corresponding edges. In that case, we can map the vertices of our graph as the sampling positions, as well as we can use the spatial distance between sensors as a means to define the corresponding edge weight. So once we have our structure in model domain, we can compute its graph counterpart, and finally try to purposely scale its modal shape related to each cluster in a way that maximizes the global graph signal smoothness. This is more or less summarized in this simple application in which we can see how the different clusters provide us different modal values, modal coordinates, which are then rescaled by computing parameters alpha p, each of them which is purposely refined at its iteration in a way such that, as I have mentioned, the global graph signal smoothness may be maximum. And once we have retrieved such a kind of information, we can obviously enter the final validation stage in which the alpha status of the structure is computed by resorting to the classical metrics, which are modal dependent, such as MEC or frequency deviation. So that is a brief list of brief references in which you can find more detail about what are the topics I have previously presented you. But before leaving you, I would like to have just a brief presentation on how that kind of sensor may behave in practice, since I have introduced you before. I will try to change my screen, so I hope I don't miss anything. Okay. So, are you able to see another screen? Or...
Yes, it's the MATLAB code now.
Okay, perfect. Okay. So I will activate my camera also here. So there should be two different windows with my name, and in one specific window there should be also an image with sensors. Let me know if you are able to see them or not. Otherwise, I will switch to my PC camera. No, okay.
We see your face.
Just my face. Okay. Okay, sensors.
But now it's visible. Yeah.
Okay, perfect. So these are the sensors. This is just one.
For those who want to view it bigger, you can choose Federica's video and choose pin so that it grows.
This is just the sensor node, and whereas this is just the network interface, which is another device which is used to connect the sensor directly on the computer. And in such way, we can retrieve data. Okay, thank you, Sophia. So these are the elements, and then I will try to get some accelerations from these sensors. I hope. Okay, just let me configure the network, and I will leave it working. Okay, one second. So my MATLAB screen.
Share the screen again.
Okay. Okay.
We can see it now.
Okay, perfect. Okay, I will just verify that the sensor is replying to me. Okay, and then I will gather data. First of all, I'll have a static analysis and a static acquisition. In that case, the sensor is programmed to have to work with plus or minus 2G as full scale range, whereas plus or minus 125 degrees per second as angular velocity range. And the sampling frequency is equal to 416 Hertz. Then we can move the sensor, and in that case, we can see, hopefully that there are some variations in our data. And what the sensor does every time is to substantially set the parameters as a network startup phase, and once the buffer in which it collects the data is full, he sends it back to the PC, and the acquisition can be repeated. So I just let it start again for a more challenging acquisition. Okay, so this is just another example of signal we can retrieve. And we have a different availability in terms of frequencies, resolution, according with the specs I have introduced you in the first slide.
Federica, we do see just the main MATLAB window. I don't know if you...
Okay.
Okay.
Yes.
You have a figure, yes, it has to be brought.
Yeah, I can share it with you. Excuse me, I was thinking that it was okay. This is just a simple screen in which I will share with you again as soon as it will appear. Okay, excuse me, I haven't seen that it has changed. And in that case, yeah, that's how the network can work, and we can connect up to 64 nodes in a daisy chain fashion in order to retrieve information. And more or less, okay, you should now see, I hope.
You have to share again, but
Okay.
maybe share the screen and draw the figure in the screen that is active.
Okay.
Yeah, the figure is deleted, not updated. That's why it disappears.
Okay. Yeah. The figure is, yeah.
Yes, so as long as the screen is shared, whenever it pops up, it will be there. Okay.
Perfect. And that completes my presentation. I am really honored to be here, and I hope that these topics may be of interest also for you, and to exchange information, and every feedback or suggestion is obviously welcome from your side. So thank you all for giving me this opportunity.
Thank you, Federica. I think it was a great presentation, actually very interactive. So hopefully others are also inspired by this presentation. I will stop the recording now since we have the main